Okay, so we're going to calculate the coefficient of friction. Now in this case it's the coefficient of kinetic friction as it is moving along the slope. So we can actually calculate it twice. We can calculate it when it's moving up the slope and then when it's moving down the slope. And ideally these would have the same values. It turns out that they don't quite. Okay, so let's draw our diagrams. We'll draw it for both cases. So here's our block, here's our block. Let's draw on our speed. So in this case it's moving up the slope. In this case it's moving down the slope. And so in both cases we've got the weight force acting down, mg. And we can split this weight force into components. So we've got a component parallel to the slope and a component perpendicular to the slope. So if we call this angle theta here, then this angle here is theta, and this one is mg sine theta, and this one is mg cos theta, and we've got exactly the same components here. The mass hasn't changed, so mg is the same size, and so we've got mg sine theta here and mg cos theta here. Now the other force that we have acting is friction, and friction opposes the motion. So in the top one, the frictional force is going to be down the slope. In the bottom one, the frictional force is going to be pushing it up the slope, so this will be our frictional force. Now to get the magnitude of our frictional force, it's given by mu k times the normal force. And the normal force in both these cases is equal to the magnitude of the weight force perpendicular to the plane, which is this mg cos theta. So this is equal to mu k mg cos theta. And it's got the same magnitude in the bottom case, but the opposite direction. Okay, so let's define down as negative. Okay, I should say down the slope. So that way is negative and that way is positive. Okay, so let's use Newton's second law to write down an expression for the forces acting in each case. So in the top case, the acceleration is down the slope. So we've got minus ma is equal to, now we've got two forces acting down the slope. We've got minus mg sine theta, that component of the weight force pulling it down the slope, and we've also got the frictional force. So this is equal to minus mg sine theta, and then we saw over here that this was minus mu k mg cos theta, and that's equal to minus ma. Okay, now all these are acting in the same direction. So the negative signs all cancel out. The m's also all cancel out. And a is something that we've actually measured. What we're trying to find is mu k. So let's rearrange this. We've got mu k times g cos theta is equal to a minus g sine theta. So this tells us that mu k is equal to ag. So this tells us that mu k is equal to a minus g sine theta over g cos theta. So now let's just substitute in the values that we're told. We know that the acceleration down the slope is given by 7. Then we've got minus 9.8 times sine 23, because theta was 23, over 9.8 times cos 23. And solving this on the calculator, we end up with 0.351, which is equal to 0.4, just to one significant figure because everything was measured very roughly. Okay, now let's compare this to down the slope. Down the slope, we've got the acceleration once again down the slope. And in this case, the weight force is down the slope, so that's minus mg sine theta. But then the frictional force is at the slope, so we've got plus the frictional force in this case. So this is equal to minus mg sine theta plus mu k mg cos theta. and that's equal to minus MA. Let's cancel out the M's once again, and then we can rearrange once again to get mu K. So mu K is equal to G sine theta minus A over G cos theta. And then we can substitute in, so we've got 9.8 times sine 23 minus 0.5 over 9.8 times cos 23, and which, when we put it into the calculator, we get 0.369, which to one significant figure is 0.4, which is the same as we got before. So this tells us that the coefficient of friction between our block and the slope is 0.4 in this case.